In this second example, we will examine a P&ID of a hydrogen delivery station. As you can see, this P&ID is really a pictorial representation of this hydrogen plant. Let's start our way from left to right. We began by identifying the main process equipment, then by identifying the main flow paths and auxiliary lines. Then finally examine the safety and emergency responses depicted on this P&ID. Here you can see the hydrogen delivery truck or trailer. It is equipped with many tubes and only one inlet. This trailer is connected to the delivery station at this level here. But the P&ID does not provide additional information as to how the connection is made. Perhaps this is the subject of a dedicated P&ID. Why is that important? Because the fluid being handled here is hydrogen, which is an extremely flammable gas, and we need to know how this connection is ensured so that we know how to handle emergency situation in case of connection failure or loss of containment. These information are not illustrated on this P&ID, but I'm pretty sure there is a separate P&ID that covers this aspect in details. Okay, so once the trailer is connected to the process, the hydrogen flows through this line, which is tagged here. From this tag, we know it has a nominal size of 3/8 inches. It has a minimum pressure rating of 3000 psi, and we know that it is not insulated. The first process equipment that the hydrogen will encounter is a valve, HV100. From the tag and the P&ID symbology, we understand that this is a hand valve, so manually operated. Then you can see here a check valve, FSV100. And in fact, to be more accurate, this is a check stop valve. Recall the little dot that you can see here indicates the inlet of the valve, and so the direction of flow. Now, between these two valves, you have a process connection to a pressure indicator, PI101, and to a pressure transmitter, PT101. This is to measure the pressure of the hydrogen line. Notice here that these pressure instruments are not involved in any control loop or safety loop. So basically here, it is just to monitor the pressure of the line. The P&ID symbols for these pressure instruments have a divider or a horizontal line running across the center of the circles, which means that they are board mounted. Now, moving on further to the right, we have an air-actuated valve. Recall from the legend and specifications P&ID we saw in the previous video, we know this is a spring return close, meaning the valve is kept open by the action of air and is closed by the action of the spring as soon as the air source is shut down. On this P&ID, the air inlet to the actuator is on this side, and the spring is depicted here. We'll come back to this arrangement later on. Now note here the presence of limit switches or position indicators ZSO100, ZSC100, and ZI100. Recall, limit switches are used on valves to indicate the actual position of the valve. ZSO tags the open position of the valve, ZSC the closed position, so O for open and C for closed. Downstream of the valve, the flow of hydrogen is split into two pipes, one going to the section of the compressor, the other bypassing the compressor. Now be careful here. You may think of this line as a recirculation line to provide a minimum flow for the compressor and prevent it from surge, as we have seen in a previous video. but the presence of this check valve FSV200 indicates that the flow path is in this direction. We can tell this based on the dot that you can see here, which indicates the inlet of the check valve. So this is not a recirculating line, but a bypass line. On this bypass line, you have a flow valve FV101, which is also air actuated with spring return close and equipped with limit switches. On the suction line of the compressor, you have a process connection to a second set of pressure instruments, PI202 and PT202. This is to monitor the pressure on the suction side of the compressor. Here again, these pressure instruments are not involved in a control loop or in a safety loop. Now notice here the presence of two valves on the instrument connection to the process. This is done in order to allow the maintenance team to safely change or check the instruments in case of failure. For example, if the maintenance team needs to change the pressure transmitter, the operator will close the hand valve HV202, then opens the drain valve that you can see here to vent and drain all trapped hydrogen in the connection between the hand valve HV202 and the pressure transmitter. By proceeding this way, the maintenance team can work safely. For additional safety, the operator should continue to monitor the system during the work. In case of any even small leakage through the open drain valve, the maintenance work should be stopped immediately and the drain valve closed. Next, on the process flow path, you have a compressor tagged CNH300. This is a multi-stage compressor as indicated here. The P&ID does not tell you the type of compressor involved in this process, but an educated guess, and based on my industrial experience, this is a reciprocating compressor. Recall, reciprocating compressors fall under the category of positive displacement compressors. Also here you have details on the compressor motor and heater. You can see inside the compressor symbol two pressure relief valves. These valves are installed to protect the interstages of the compressor from overpressure. Now, since this compressor is a multi-stage compressor, we can expect that it has 3 stages. Why is that? Because this first pressure relief valve is certainly installed at the discharge of the first stage to protect the second stage from overpressure. And this second pressure relief valve is certainly installed at the discharge of the second stage to protect the third stage from overpressure. So there are 3 stages, therefore making this compressor a 3-stage compressor. And you are able to figure this out by simply examining the symbols on the P&ID. This is why P&IDs are so powerful. These two pressure relief valves have a common discharge line. In our case here, the excess hydrogen gas is routed to a safe location 10 feet above the ground. The circuit that you can see here is the compressor cooling circuit. Because compression is an exothermic process, the compressor should be continuously cooled down to remove excess heat. So here, this cooling system is basically cooling water in a recirculating closed loop. The cooling water is conveyed by the centrifugal pump that you can see here, tagged CW800. The water circulates through the casing of the compressor in a dedicated jacket to cool down the compressor. Then this water passes through 2 water chillers in series, GW800 and GW801, to be cooled down, then re-injected in the compressor jacket in closed loop. Once compressed, the hydrogen gas exits the compressor and flows through a 3/8-inch line with a minimum pressure rating of 15,000 psi. So this information is basically telling us that the compressor in this process compresses the hydrogen from 3000 psi to 15,000 psi, therefore providing a pressure ratio of 5. That is 15,000 psi, the discharge pressure, divided by 3000 psi, the suction pressure. The compressed hydrogen gas flows through the filter FF300, then a check stop valve FSV300, then a hand valve HV301. Past HV301, the flow of the compressed gas and that of the bypass line are merged, then routed to 4 possible locations. It could go to 3 identical storage tanks, PBNH 401, 402, and 403, or go to feed hydrogen nozzles downstream. Let's first focus on the storage tanks. Now, these are identical arrangements. In each case, first you have an air-actuated valve with limit switches, then a process connection to pressure instruments, then a hand valve, and finally the storage tank. In this P&ID, you don't have details related to the storage capacity of the tanks. We don't know their design pressure, and we don't know their design temperature. Perhaps there is another P&ID depicting these storage tanks with more details. Also note here the same isolation system on the pressure instruments to allow safe maintenance operation. Now let's examine the other possible flow path for hydrogen. In this case, the gas is not sent to a storage tank, but to downstream high-pressure nozzles for process use. So first there is a hand valve HV400, then an air-actuated valve FV400 with limit switches and position indicators transmitted to the control room. Then you have a hydrogen dispenser. Here the flow of hydrogen is split. The first part of the flow feeds a high-pressure nozzle. The second part is routed to a heat exchanger to cool down the hydrogen. We know this because the other medium involved in the heat exchanger is continuously recirculated through a chiller. The cooled hydrogen then feeds a second nozzle downstream. Okay, so now we have examined the main flow path and identified the main process equipment. Let's have a closer look at this part of the P&ID. These equipment are in fact not part of the process, but rather part of the safety system. Their main function is to provide instrument air to the actuators of the valves on the process side, to keep these valves in the open position. Recall the line symbols that you can see here, so slashed lines represent pneumatic lines, or lines conveying instrument air. The first equipment in this system is an air compressor. From the symbol, we can guess it is a liquid ring compressor, so a positive displacement compressor. The compressed air feeds a surge vessel PBAL100, then a filter AF100 to trap all residual materials and purify the air. Then it goes through an air dryer AF101 to get rid of potential moisture and humidity. This is done in order to provide dry instrument air to the actuators downstream. If the air contains moisture, it will condensate, and water will damage or prevent the good working of the actuators. Now, why is this system part of the safety system? How do we know that? The answer is quite obvious. The instrument air is supplied to single-acting spring-return close actuators on the process valves. This means that these valves remain in the open position as long as the actuators are supplied with instrument air. As soon as the instrument air supply is cut off, the process valves will be closed by the action of the springs. So imagine the plant is operating under normal condition, one trailer is connected and hydrogen delivery is in progress. Then, out of the sudden, an operator detects a hydrogen leak, let's say somewhere here. An emergency response to this is to shut down the air compressor. This will stop the instrument air supply to all of the actuators, which will immediately close all the process valves, therefore providing containment of the hydrogen trailer and preventing any further hydrogen leak and its associated hazards. To finish off this video, on this P&ID, we can see a fire and gas detection system in two locations, one at the trailer connection, as depicted here, and one at the process nozzle connection. In both cases, infrared flame detectors are used.